This lesson is 5.5, College Algebra, page 482, Inverses of Matrices. Alright, so what we're going to do is working at finding the inverse of a square matrix, if it exists, and we're going to use those inverses to solve systems of equations. And I think you'll find that by doing it this way, it is a little bit easier. So recall that for all numbers, if we have a number, say 5 times 1, that also equals 1 times 5. And y, or the 1 is a multiplicative identity, meaning if we multiply it by 1, we're going to get our original number back. So, a multiplicative identity matrix is very similar to the number 1, but we're just going to use it when we're talking matrices. So if we're talking a square matrix where the number of rows and the number of columns are the same, and remember using Gaussian elimination, we had all this information here, and I guess Gauss-Jordan is more what we're doing here by changing everything to zeros except the main diagonal. For any positive integer n, the n by n identity matrix is an n by n matrix with 1's on the main diagonal and 0's elsewhere. So this whole thing is considered the identity matrix. So if we have a matrix like that, a 2 by 2, so it's a square matrix, and we multiply it by its identity matrix, so we're going to multiply it by a matrix that has the same columns and the same rows in it, so it's the same name. If we multiply it by its identity, we should get back our original. So it's just like you take 5 times 1 and get 5. We take this matrix times its identity, we should get this matrix back. So remember from the other day, from 5.4, I think it was, when we multiplied, we just had our identity matrix, and we look at this as a 2 by 2, and this is a 2 by 2, and it's doable, and it's going to give us a 2 by 2 matrix. Okay, and so remember, we look at this, we want to put a number here, so we're going to take this row, first row, times the first column. So 4 times 1 is 4. Negative 7 times 0 is 0. So 4 plus 0 is going to give me a 4 here. And I keep going, and I'll end up with these numbers back, which is shows that it's my identity matrix. And if we flip those around, if we took this and put it in front of here and did our multiplication, it would still work out. So we're okay doing identity matrices either way, whereas other matrices you can't do that because they're not commutative. So if you remember from olden days, if you've got a multiplicative inverse, you've got 1/3. The multiplicative inverse is 3 over 1. And that's going to equal 1. So anytime you take a real number and you multiply it by its inverse, you're going to get a 1. When you're doing inverses of matrices, you're going to have the same thing happen. When you multiply them out, you should be able to get 1. So what we're going to do is we're going to name a matrix as A, and we're going to name the inverse is a to the minus 1, or we're going to call that A inverse. Okay? And not every matrix has an inverse. So let's take a matrix such as 4, negative 3, 3, negative 2. And let's prove, let me get rid of some stuff here. Let's prove that that inverse that we just drew there is the inverse of negative 2, 3, negative 3, 4. Now notice it doesn't look anything like this one. I mean, they look completely different. They have the same numbers in them, but you would never just be able to look at it and say, oh, this is the inverse. So this is the original, and this is the inverse. So what we're going to do is we're going to try to show that this is an inverse of that. So what we're going to do when we take if they're inverses, when we multiply them, just like the number 1/3 times 3 over 1, when we multiply those, we get 1. We get the identity. Okay? So when we multiply these together, we get the identity. So it should show that if we multiply these two together, because this is the inverse of this, we're trying to prove that if these two are inverses, if we multiply them like we did here, we should get the identity. Okay, and remember the identity when it comes to a matrix, like a 2 by 2, the identity is 1, 1, 0, 0. So what should happen is when I multiply this times this, I should get this. Okay, so let's go ahead and let's name this, just so I'm not saying this and this. Let's name this a capital A, and let's name this one a capital B. Okay, so let's get rid of these, and so if we take A times B, so one number times its inverse, we should get the identity matrix. But what also is true is that it has to be true is that the opposite needs to hold. So if we multiply matrix A times matrix B, that should give us the same answer as matrix B times matrix A, and that same answer is this one right there, the identity matrix. We should get 1, 0, 0, 1 when we do that. So let's go ahead and use Gauss-Jordan elimination in order to do that and see if that happens. So let me clear this up a little bit. Okay, so the book said that these two matrices were inverses, my A and my B. And if that's the case, then I should get as an answer, when I multiply those, 1, 1, 0, 0. I should get that. So if you go ahead and do the math, you'll find out you get a 2 by 2 matrix. And you're going to we're going to first of all, find this one, and this one, and this one, and this one, and we'll just do one of them here. Let's find this spot right here. So I take row 1, column 2. Row 1, column 2. 4 times 3 is 12, plus negative 4, or negative 3 times 4 is negative 12. Positive 12 plus negative 12 is 0, and that's what I want, my 0 right there. And I keep going, and you will discover that you get the identity matrix. And since you get the identity matrix, you know that these are inverses. But you're not done yet, because you also have to do it the other way. You have to switch them and do the multiplication this way too, because if it doesn't work both ways, it's not one is not the inverse of the other. So then I have to do it that way and see what I get for an answer, and sure enough I get this again, so therefore it is the inverse. So AB equals the identity matrix, and BA equals the identity matrix, and since they both work, we know that B is the inverse of A.